Okay, so we're doing Descartes' rule of signs. So another little, I want to say like tip, to basically find the zeros of a polynomial. So it's not a foolproof method like synthetic division, figuring them out. Kind of like the rational zeros test where it's going to give you like the possibilities. So not the greatest thing, but it's still helpful. So basically, you're given f of x. Then the possible positive zeros are the number of sign changes. And I'm going to say unless by 2. So this only gives you the positive zeros, unfortunately. The negative zeros work the exact same way. I'm not going to write the whole thing, but you find the number of negative zeros. From the sign changes of f of negative x. So we'll be looking at a polynomial, figuring out when it changes from positive to negative, negative, positive. Counting all of them up, it gives you a possible number of positive and negative real zeros. Okay, and once we know the positive and negative, we kind of make like a guesstimation of the imaginary zeros or the complex zeros. Okay. Yeah, so if we have like 3 different sign changes, then I could have 3 positive zeros, or I could have 1 positive zero by subtracting my total by 2. Yeah, so that's where it gets a little funky. So it's not a foolproof method to get this, because there's different options. So yeah. Here's our first example. So finding the positive isn't too bad because they give you the polynomial already, so you just have to count them up. The negative one, you have to do like a little bit of work. But it's still not too bad. We're going to make a table to like organize all our possibilities, basically. Okay, so if I'm doing the positive, just looking at the polynomial, I can count the number of sign changes. So from x to the 4th to negative 6x to the 3rd, that's a sign change that changed from positive to negative. So that's 1. And then I go from negative 6 to positive 8. That's a second sign change. 8 to 2, I don't change signs, so that doesn't count. But I can do 2 to negative 1. That's another sign change from positive to negative. So for the positive possibilities, I could have 3 positive real zeros, or I can do less by 2 and have 1 positive zero. So that's how you do positive. So you count the possible sign changes. So then you have 3 total, or you could have 1 when you subtract 2 from it. That's what the less by 2 means. So you can have 3 positive or 1 positive real zero. Okay. So doing negative, I need to figure out what f of negative x is first before I can count the sign changes. So I'm going to replace every x value with a negative x value. And then we'll simplify it down. Right, so every x replaced with negative x. So if I'm working with this, negative x to the fourth power, so what does an even exponent actually do to this negative sign? Yeah, basically it changes it back to positive because I have 4 negative 1s basically, and that becomes just a positive number. If you have an odd exponent, it's going to stay a negative sign, so you have negative 1 3 times. So then this term will change to plus 6x to the third power. So you have negative 6 times that negative 1. The 8x squared stays positive. And then 2 times negative x is negative 2x, and then minus 1. So now here's f of negative x. I can count the number of sign changes. So there's only 1 from 8 to negative 2. So basically the possible negative zeros are just 1. Okay, so let's make a table to represent all of our possibilities. What did I say for non-complex? Yes. Okay, so basically I could have 3 positive real zeros, and I could have 1 negative real zeros. How many total zeros should I technically have for this polynomial? 4, because my highest exponent was 4, so there should be 4. So that means if I have 3 positive and 1 negative, I should have 0 complex, like 0 imaginary solutions. But I have another option. I could have 1 positive. I will always have 1 negative no matter what. Yeah. So now I have 2 complex or imaginary solutions. So that way my whole row adds up to 4. So there's my table. Not too shabby. I mean, if you know this, it might make it easier when you do an irrational zeros test to figure out should I be testing like a positive number or a negative number based on sign changes. Cuts your plus in half anyways. Okay, here's our last one. So, we're going to be pros at finding zeros. So it says find all complex zeros of each polynomial function, give exact values, list multiple zeros as necessary. So complex zeros mean I could have real zeros. So like a whole number, a fraction, we could have a square root type of situation, or we could have imaginary zeros. Exact values means no decimals, so they should all be simplified square. Yeah, so the last part of the homework assignment I give you, there's different problems. So either you can find the zeros of the polynomial by factoring, which is what you should always try and do first, because there are some that can factor. And then doing like rational zeros test and synthetic division is like the next easiest option, I guess. Unfortunately. So this one, can I factor this at all? No. So when there's 5 terms, not really. There was 4 terms, you should try and cut it in half and factor by grouping. Even if it's like a higher, like x to the 6th power, you should still try and cut it in half with those 4. So this one, we're going to do a rational zeros test. Then do synthetic division. We just have to find one that works first. It goes in there. So I mean, I'm looking at the polynomial. If I like apply Descartes' rule of signs, I have 1, 2, 3 different sign changes. So I know I have to have a positive real zero, 3 positive real zeros, or 1 positive zero. So if I did the p over q thing, just to start us off, what's my p value? What's my q value? Yeah. So then remember I have to write the factors. 1, 2, 4. I don't know, so maybe you just start with like 1 C. I always like to start with 1, I think that's nice. One works, right? Yeah, that's how I like to start with 1. So we do synthetic division. 4. Okay, so then you can drop the 2 down. Got a remainder of 0, so that's just next year insurance policy. You know, it does work out. So right now I should have a cubic. So I could write it as the whole cubic if I wanted to. The only reason why I'd write it as a cubic is if I could factor it. So is this factorable if I wrote in the x to the third, x squared, and x? Yeah. So you can rewrite this. So there's 4 terms, so we can cut it in half factor by grouping. Most of the times that doesn't work out that way. This one was just kind of nice. If it didn't work out, you'd have to do another fractional series test, figure one that works. Okay, so my cubic polynomial factors to be this, which is helpful. Technically, I have like another 0x minus 1 from the 1. If I wanted to write the true f of x polynomial, so I have all of the linear factors. Okay, but I could set all of these parts equal to 0 to find the rest of the zeros. So I can have x squared plus 4 equals 0. 2x plus 1 equals 0. And I already know x minus 1 equals 0, so give me a 0 of 1. That's the one we tested. Solving for x on 2x plus 1, I should get out -1/2. This x squared plus 4 is more interesting. Subtract 4 both sides. Then we square root both sides. So what is my solution? Yeah, plus or minus 2i. So I get out the 2 solutions. So I get out 4 zeros, which I should get out 4 because it was the 4th root. Yeah, so we got a positive 0, a negative 0, and 2 imaginary zeros. Fun times. Okay. So tomorrow we're going to start graphing. So exciting.